So if you see a certain kind of op amp, what it can tell you is, if you recognize it, it can tell you the relationship between the output and the input. So like on this first one, this non-inverting amplifier, what that A equals 1 plus R2 over R1 means is that if Vin is 5, then V out is going to be 5 times, open parentheses, 1 plus R2 over R1. The follower, you can see that the gain is just 1. So your input, your Vin, is the same as your V out. The inverting amplifier, you can see that that one is negative. So that's the inverting part, is that it's negative. So the gain is minus R2 over R1. And the summing amplifier sums the V1, V2, V3, but it doesn't just sum them by themselves, it also has the resistors in there. So if you recognize one of these op-amp circuits, then you can see what it does. And I think this is on the next page of the handout. Yeah, so this is, I thought this was really nice. This is one, again, that your professor put on your PowerPoint that's just a little easier to use, so she labeled it differential amplifier. So it gives you the difference of V2 minus V1, and the one that your book has as a subtracting amplifier, it's a little harder to see how it actually subtracts. But this one, you can see what the output is based on the input and your resistors. Notice that in this picture here, R1 is repeated. So this R1 and R1 are the same, and this R2 and R2 are the same, and that's why we get this as opposed to the one from your book. So this is the chart from your book of some different op-amps. So we have the non-inverting op-amp, which we have that, it is the same as the non-inverting amplifier that you had on the first page. It's just kind of written in a different sort of way. And it notes that it's independent of this first resistor that's there. And then you have the inverting amplifier. And again, if you just look at it, it might be drawn a little differently. Actually, it looks like this one's drawn this out. So, but there can be, you can just look at them and see how they are related. And the G here is for gain. And then we have the inverting summing amplifier. And if you had noticed on the first page, it was a sum, but it was also inverted. There was the negative there. And then we have the subtracting amplifier. It looks a lot more complicated than the one we saw here, but that's because this one, R1, R2, R3, and R4 are all different. If you made R3 equal to R1 and R4 equal to R2, you'd have the same as the differential amplifier. Oh, actually, I think it's on the bottom of this page on the handout. And then we have the voltage follower, and the non-inverting summing amplifier. So that one's nice and complicated. So that one does not have the minus sign. So the main reason for these is just if you see them. So if you see a problem that has one of these and you recognize it, then you'll know what to do with it. But what you really need to know how to use are the properties of an ideal op-amp. And the properties of an ideal op-amp are what you're going to be using to solve most of these problems. So the properties are, let me draw this. Just draw a random one here. . 。 . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . I don't know what that does. We could figure it out. Okay, so we have, this is IP is the current going into the positive terminal. IN is the current going into the negative terminal. And in an ideal op amp, and that's going to be almost always the kind you're dealing with is ideal ones. IP equals IN equals 0. And so you'll use that when solving your problems, that current is 0. The other biggie is that the voltage here, call that VP, and the voltage here, VN. VP equals VN. Doesn't have to be 0, but they do have to be equal. That's really it. The other parts of the ideal op amp have to do with the internal makeup of the op amp, which I'm suspecting you're not really going to have to know much about, but I'll show you a little bit of it. Okay, there are also a couple interesting op amps that do calculus. So the first one we have here is the Integrator. Now, y'all haven't done capacitors yet, right?
I think we just started. We started on it yesterday.
So you started chapter 5, which does have capacitors in it. Yep. Okay. So here you'll learn that you'll learn about capacitors in this chapter, and I'm drawing a blank on what I was going to say. But I think on this last thing here with V out, I think there's a typo. I think the idea here was you integrate both sides and you get that V out equals minus 1 over RC times the integral of Vn dt, because the integral is missing there. And then there's the differentiator as well. And you'll be dealing with RC circuits in this chapter, so you'll learn more about those. Probably not too many with op amps in them. Okay, so again, those are mostly just for you to recognize. I'm going to talk just a little bit about non-ideal op amps, and we'll do a couple problems with them, and you'll do more with these next semester. Don't most people take circuits 2 and electronics at the same time? Yeah, maybe, yeah. Okay, so this is kind of sort of a picture of what an op amp looks like on the inside. You don't have to really know much about it at this point, but the idea is that if we had an ideal op amp, that this resistance would be infinite, and this resistance would be 0, and A would be infinite. And at this point, it all just kind of seems like magic. Okay, well, how does this work? And it does, and you will learn more about it. Now, VCC, that is the voltage that is coming into the op amp. So like if you were plugging it into a circuit board, that would be the voltage that was coming into it. And if these two equations here go for any op amp, and this A is not the gain, it's not the amplitude like on the first page. So VO equals A times VP minus VN. Now, we said in an ideal op amp, VP equals VN. And so this would be A is infinity, and VP minus VN is 0, so infinity times 0, well, obviously that's indeterminate. So This would be like a real op amp and not an ideal op amp. And the other thing to be aware of is that VO, your output voltage, has to be between plus or minus VCC. And like I said, VCC is what you have plugged in. And we never had to know much of this at all. Oh, I lied. Apparently A is the open loop gain or op amp gain. Okay. They just use A, they use A here in the book for this, and then they use G when we're talking about our real op amps. Okay, so when you have an op amp, what you're going to be looking for is a high input resistance, so that's this resistance right here, and a low output resistance, and a high open loop voltage gain. And that's just saying these things right here, which you won't really have to deal with. But what you might have to deal with is a problem that has to do with the range of an op amp. And I don't think I put this picture on your handout for some reason. It is in your book. And this has to do with the fact that VO has to be between VCC and minus VCC. And so our x-axis here is VP minus VN. So that's the difference between our positive and negative, which an ideal op amp is 0. And the y-axis is VO. And you can see that VO never can get above VCC or below minus VCC. So it is possible that you might have a problem with that, because there are problems in the book like that, and we will work one. So, all right, any questions to this point? It's all fascinating, I'm sure.